Potential head. This is our pressure head and velocity head, or your dynamic head. Right? Right? And together they call your total head, right? Or basically your total energy. Right? Because we call it head because we can represent all of those different forms of energy. We can represent them in terms of a height. Right? And this is what Bernoulli's principle. We don't have no energy loss here. We're assuming no energy losses, no losses. But we can also have, where we look at pipelines now, rho J plus V1 squared on J, V2 plus V2 on J, V2 squared on J, plus our losses, right? Right, our H, which you can call our H, or HL if you want, which is our shock losses, plus HF. Right, we have other losses and so on. I'm not, right? Or your roughness in the pipe and so on and so on and so on. Right? So this is what we're going to be looking at. Right? So we want to look at, let's look at some of these questions. I'm going to start with number 2. Right? So we have a 200 millimeter pipe. Right? It's carrying, let's draw it first and then we put in the pieces, right? So you say we have a 100 millimeter pipe carrying blah blah blah. It enlarges, right? So it starts off at one size and then it enlarges to another size, right? And then they say find the loss of head due to the sudden enlargement, the difference in pressure in the two pipes, right? In the two pipes taken between points just outside the area of the disturbance of the section, right? Right, so if we call this point 1 here, and somewhere point 2, right? Because we're going to have some disturbance inside of that area here, right? Then you see the corresponding difference in pressure if the change in diameter were to be affected by a gradual cone, no loss, right? Assuming no loss, right? The axis of the pipe is horizontal, right? So we want to find, so we told that number 1 we have 100 millimeter diameter. Number 2 is what? 150 millimeter diameter. They give us the flow rate. It's going to be 1.8 cubic meter per minute. You could change that into 1.8 on 60, right? And how much is that per second? 0.003? Yes. Yeah? 0.03 meter cube per second, right? So we want to find the loss of head due to sudden enlargement. Right? How do we find that? Do we need Bernoulli equation?
No, we get it V1
yeah, so yeah. So what's it then?
V1 divided by 2G.
Yeah? Over 2G, right? So how are we going to find V1 and V2? The continuity, right? Yeah, because we know Q, right? And we know the diameters. Yeah?
Yes, sir.
So we can say Q is equal to AV, A1 V1, which is also equal to A2 V2. Right? So we can find the velocity, so we can say that Q is equal to G1 squared pi V1 squared on 4V1, right? And then we can say, okay, our V1 is equal to 4 times Q on pi V1 squared, and same thing, V2 is equal to 4 on pi Yes? Yeah?
Wait,
So we just solve for V2 and plug it back in.
We need V1 and V2,
Oh,
because this is the loss,
okay.
right?
Yeah.
Alright, so once we find V1 and V2, you plug it in, and you should get this answer. So let's find it, let's see, let's just at least do a check on ourselves. Alright, V1, 4 times 0.03 on pi, V1 is 100 millimeters, alright, so 0.1 squared, V2, 4 times 0.03 on pi, 0.15 squared. So somebody with V1 please, V2.
V1 is 3.819.
V2 is 1.697. 1.6. 1.7.
Oh, 1.7, okay?
Yeah, okay, right
Right, so then, our HL now, our head loss, V1, which is 3.82, minus 1.7 squared on 2 by 9.81. Anybody with an answer?
now. 0.229.
Yeah? Anybody else can double check that?
Yes, sir.
Alright, and that's the answer right there. Right? Right. Now, the pipe is horizontal, right? So again, if we apply this principle, right? Here. Now remember, we have, if we were to apply this principle here, between 1 and 2, how will you write this equation?
P1 over gamma.
Let's start from Z1.
Z1
Mm-hmm.
plus P1 over 2 on 4G. Plus V1 squared on plus P2 on plus V2 squared from 2G
Mm-hmm.
plus
Plus V1.
Oh.
Oh, yeah, in terms of that, right?
Yes?
Yes.
Are you with me? Anybody confused by that?
No.
Right? Plus the losses, right?
Yeah, the head loss.
Because we have a loss, right? So what can we start eliminating from this now? Z1 and Z2, right?
Yeah.
Z1 and Z2, right? We can start eliminating that. What does the problem say? It says down. It says B, right? The difference in pressure in the two pipes, right? So we want the difference in pressure, right? So basically what we want? We want P1 minus P2.
Yes.
Yes? Right? So we want P1 is equal to V2 squared on 2G minus V1 squared on 2G plus V1 minus V2 squared on 2G. Yes? Yes or no?
Yes.
Yeah. Right, so P1 minus P2 on rho G is equal to 1 over 2G V2 squared minus V1 squared plus V1 minus V2 squared. Yes? Yes or no?
Maybe so. Yeah.
So P1 minus P2, I can carry this over I'll have rho G, so all I'll have here is rho, right?
Yeah.
Yes?
So you cancel out the G's?
Yeah, I carried this over. Can you see that? I'm working too fast.
You going
What
too
about
fast?
this one?
So down.
1/2.
So it's a half, right?
Yeah.
So it's rho on 2, right?
Yeah.
Okay. Alright, so v2 squared minus v1 squared, right? Plus v1 squared minus 2 v1 v2 plus v2 squared, right?
Yeah.
Just breaking this down as much as possible. Right, so what do we have? So p1 minus p2, rho on 2,
So if you want to,
so
V2
this gone, right?
Yeah.
Yes, so it's 2 v2 squared minus 2 v1 v2 plus, yeah, that's it. So now I can have p1 minus p2 is equal to rho into v2 squared minus v1 v2, yeah? Yes? Right? So that's when, so we know what, we already have v1 v2, right? You already did that. Yes?
Yes.
Right? So P1 minus P2 is equal to rho, which is what, 1,000?
Yeah.
What was V2?
1.7.
Right? 1.7 squared minus what? 1.7 by 3.82.
82.
Right? Or maybe I should have P2 minus P1, right? So you might get a negative answer, right?
Wait, is that 1.7 or 17?
1.7.
Oh, yes.
36 so far.
Hmm?
Negative 36 so far.
0.4?
36 so far.
Yeah?
Yeah.
Right? But it should be P2 minus P1, right? But you can see we get 3.6, right?
Yeah.
Yeah?
Yeah.
Right? But it's just the other way around,
Yeah.
right? And this should be kilopascal, right? Pascal, sorry, just Pascal. Right? PA. So it is negative 3.6 kPa. Right? Or 3.6, right? It's just that we have it reversed. We should have done P2 minus P1. Right? But the answer is still the same, yeah.
Say if this was an exam question and it would be negative, would you notice? I mean,
I'll give it to you, right? You just have to recognize that.
Okay.
That you have it switched around.
Yeah.
Alright. Okay, next one. So they said, the other part of the question is saying, third part, the corresponding difference in pressure if the change in diameter were to be affected by a gradual cone. What does that mean?
No loss.
No loss, right? So if there was no loss, right? If there was no loss here, what would our equation be?
Take away the V1 minus
This
V2,
disappears.
yeah.
Right?
Yeah.
This goes,
Yeah.
right? So now, if that goes, and I'll remove this.
You didn't get it? I got it.
Right, so that goes, so we end up with 1 minus P2 on rho G is equals to, let's see, so V1 on 2G, right? V1 minus V2 is equals to rho on 2 V1 was what, 3.8? 3.82 squared.
Isn't it V2 minus here? Cause you're moving the one over?
No, I'm carrying the V1 over. I'm bringing P2 this way.
Correct. So you have P1 minus P2, V2.
Oh, okay, yeah, all right, yeah, you're right, my apology. So this should be V2 minus V1. Alright, so you switch it. So this would be 1.7 squared, right? And we'll end up with a negative answer as well. Yes? Right, but it should be negative, it should be 5,000 and something, right? Yeah?
Yes. 5.85.
And really, to be honest with you, that's actually correct, right? Because really, you are getting a pressure drop,
High as well.
right?
Yeah.
Because your velocity, your speed is going to slow down.
Yeah.
Right? Which means your pressure has went up or down.
It's going down.
So wherever you have the higher velocity,
It's high to low.
right? High velocity means you have what?
No pressure.
Low pressure. So actually the pressure went up. Right?
Yeah.
Right, it actually went up. So so one thing I want you to appreciate in fluid mechanics, where you have very high flow. High flow means you have low pressure. Yes, I know what I'm saying. Right? So something's moving really fast, fluid is moving really fast, you have low pressure, not high pressure. Right? So, in your velocity is going to be moving faster or slower here?
Faster. No, slower.
Faster or slower? Slower.
It's a bigger area. So it's gonna-
Okay, yeah, that would make sense.
Higher or slower? You sure?
Slower. Cause there's more.
Slower.
Yeah.
So,
But
no
it's
pressure
slower
is
with
not
higher
negative.
The pressure is higher there. But the pressure is
Higher
higher.
pressure, isn't it moving fast?
so low pressure is moving fast, right?
Yeah. Is it like kinda like
Alright, let's think about it.
Yeah.
Right?
That's what's missing.
So let's think about it. So my area here is what?
Why?
My area is higher, right? So my V would be small. Right? So my area here is low, my V is
High.
high. Right? So my pressure here should be what?
Low.
You saying that my pressure here would be high or low?
Low.
Low.
Higher.
Okay, well, let's see.
Low.
You say high. We will say low, right?
It's like a pressure.
But then why is P1 minus P2 negative?
It makes sense, yes, but it's just logically.
No, I'm not going to tell you wrong, man.
It's low to high.
Right? Because if P1 was higher,
Then that'll be low.
this should be positive, right?
Yeah.
So really, your pressure here is low. Right? So anytime you have low pressure in a system, your flow will be high. Right? If you're going from a high pressure to low pressure, your gas flow, your fluid flow is going to go crazy.
So crazy.
Right? If you're in a gas plant and you hear you can hear the flow moving really fast, you know you have a big pressure drop somewhere. Big pressure drop. So here, right? And so you have a big pressure. This is a big pressure drop system here. Now it didn't tell us, right? Right? I think it does, we don't know. I don't even know if what direction this thing is flowing. It doesn't tell you. So really it could be going this way. Right? But the fact is we know, since we have P1 minus P2, that P2 has to be bigger.
Okay.
Yes? Yes.
Going back to like the direction, if we were going the other way, would we change our HL? It'd be a different type of launch stop, right?
Of course, because it would be going to a
But we would still get the
construction.
same answer or no?
For pressure.
In terms of like the,
I'm not sure, but the equation would be different, your law. So it would be different. You get a different answer. Wouldn't be the same answer.
okay.
Right? So to your point, you're right. We're actually going this way. Right? Okay, let's look at another one then. Right? I'll give you a chance to do number 3. And then you guys walk me through it. So we're going to look at the third question. Right? So it says water flows down a straight inclined pipe, so it's inclined. It's at a point A, 45 meters above datum. Right, the section of the pipe suddenly doubles in area. Right. The pressure in the smaller pipe at A is 860 kPa, and the velocity of flow in the larger pipe. 24 meters, find the pressure hit at point B, which is 2.5 meters above datum. So the trick in this question is how you're going to draw it, right? Because if you don't draw it right, you're not going to get the right answer. So how should we sketch this?
Small pipe getting to a small pipe.
So I start like this.
Yeah, like that. That's kind of thin, but we work with it.
Right?
And then it doubles. Kind of big, yeah. It
Then it
doubles.
doubles, right?
Yeah. Oh no, sharp.
It doubles. But it keeps going, right?
No, suddenly. So it becomes a sharp. Make it
It
sharp.
doesn't matter. I know it's doubling,
Oh.
right? It's doubling, right? So where's my datum? My datum is somewhere here, right?
No.
Yes.
Yes or no?
Yes.
Okay, so from this point to my datum
Yeah.
is what?
45 meters.
Right?
Oh yeah.
No.
Yeah.
No.
Right?
Point A is supposed to be on top.
It's supposed to be on.
Huh?
It's on top, right? It says
That
above
point
the.
A's at the top.
A is at the top because it says above it.
At point A. A is where it's doubling, right?
Yeah.
At point A, 45 meters above datum, the section of the pipe doubles in area, right?
Mm-hmm.
So my pressure in this pipe would be at point A is what? 860, right? Yes? This is D1, right? D2, so D2 is equal to twice times D1, right? Yes?
Yes.
So the pressure in the smaller pipe, blah, 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 and the velocity of flow in the larger pipe, so we know V2 now is equals to 2.4 meters per second, right? They say find the pressure in kilonewtons at A point B, right? So somewhere, some point B, somewhere down here, right? Right, it didn't tell us whether or not it's exiting or not, so we can't make any assumptions, right? 2.5 meters, right? Yes? And we want to find PB. Yes?
Yes.
Okay, what are some things they didn't tell you that you think you might have to?
The law.
There's losses. Indirect.
Loss.
Hmm?
Say, yeah.
It didn't say anything about what type of loss.
Frictional.
Nothing about frictional loss, right? So we're going to assume that there's no frictional loss.
Yeah.
Right? Then they tell us that we have a sudden expansion. So do we need to consider
Shock.
that shock loss?
Yes.
Yes or no?
Yes.
Yes, right? So how do we start off this problem, guys?
Bernoulli.
No, it's the A1. A1. Yeah, considering.
So why do you want to start off with continuity?
Continuing philosophy. Yeah, so you put it in. It gave
It
us.
doesn't matter, right?
Yeah.
So I can say PA or ZA, right? Plus PA on rho G plus VA squared is PB on rho G plus VB squared on 2G plus what?
Shock loss.
The shock loss, right? Which is
VA
VA
Minus
PB.
EB squared over 2G.
on 2G.
That's the head loss, right?
Yes. You with me, right?
Yes.
Right? Because now I have my loss in this area here because I have a sudden expansion. Right? And we can't get rid of our ZA and our ZB, right? What are we trying to find?
PB.
We need to find PB, right? Because we have PA, we know ZA, so this is my ZA here, and this is my ZB. Are they positive or negative? Positive, because they are above the data. Yeah? They're not negative, they are above my 0, right? They're not below, right? And now we need to find our VA and our VB. We don't know what they are because we need them in this equation here. So how do we find that? Continuity, right? Because they told us, did they tell us the flow rate?
No, but you can write it in terms of.
Velocity.
You can write it in terms of VB.
So my Q is equal to what?
A1, B1.
VA,
Oh, yeah.
VA, right?
Yeah.
VA.
And which is by yeah. And I can do the same for VB, which is I VB squared on 4 VB, right? And what do we know about? So if you want, you could say DA, right? So DA, let's call this DB, DA, right? So my DA, my DB is twice times DA. Yeah? It didn't tell us anything about the flow rate. And so what do we do, guys? now I can write that my pi.
Wait, I think we're wrong. Didn't it say double area, not double that area?
Yeah. Hold on,
So you can't say.
You're double the area.
So you would write it in terms of the A. The A is-
Okay, yes, you're correct. My apology. You are right. Happy you're paying attention. Right, so this is, so let me rewrite that over. Right, so that A1, so this is A1, AA, AB is equal twice times AA, right? Yeah? Right? Which makes it easy, which makes this easier. Alright, so let me do this. Is equal to AB, BB, right? So that I can write my AA, BA is equals to twice times AA, right? Yes?
Yes.
Alright, so basically my velocity in A is twice times my velocity in B. Right. So then what do I do now?
Right, then put that
So you're saying, right, I can replace,
because we had, they gave us VB.
they gave us VB, right?
Correct.
Right, so they told us VB was 2.4, right? So V, we know that VB was what, 2.4? Yeah. Just per second, therefore VA will be 2 by 2.4. 2.8 meters per second. Yeah?
Yes.
So we're in business,
Yes.
right? So we have our VA, we have our VB, right? So now I can start solving for PB, right? Right, so my ZA was what, 45? PA was 860? Right? Yeah, times 10 to the 3 on 1,000 by 9.81. VA, which was 2.4 squared on 2 by 9.81 is equal to ZB, which is 2.5.
I think VA, isn't it 4.8, because we changed it to times 2.
VA, yeah, no, I got my apology, 4.8. 4.8. It's weird, right? Plus PB, we don't know what that is, right? Over 9810, right? Plus VB, which is 2.4 squared over 2 by 9.81. VA minus VB, right? So VA, which is basically 2.4 squared on 2 by 9.81. So the only unknown is PB, right?
Yeah.
So we just have to rearrange everything and find PB. Okay. Anybody with the answer? Let's work out, let's,
Down.
so 45 plus, what's 860 divided by 10? About 86? Right. I mean, it's pretty straightforward.
Yeah.
Anybody with an answer?
1,283.
Hmm?
406.2.
Really?
What?
This is the answer here.
What?
actually 1283.
Yeah, 1, 2, 8, 2.
You got it? Yeah. So it should be 1283. So you have to be careful.
Come on, I heard.
Go. You have to be careful with these calculators. Yeah. Sometimes it's better to just work each part.
Yeah.
Right? Right, you should get that answer. 1282. Let's do number 5. I'll come back to number 4.
It's over meters squared. It's over meters squared. It's stated. And for number 3.
This is kilonewton per meter squared. Right, it's a pressure you're finding, right?
Yeah.
So it has to be. Right? So it should be 1283 kilopascal. Alright, so let's do number 5. Right? You alright?
Yes.
Some water? Okay, let's look at number 5. I'm not gonna ask you to derive anything, right? So you say water flows in a 150 millimeter pipe. What do you mean? Water flows.
Yeah, number 5.
Right, so water flows in a 150 millimeter pipe and then it expands, right? And at a sudden enlargement, the loss of head is found to be 1/2 of the velocity head. Determine the diameter of the enlarged portion, right? So, and at a sudden enlargement, the loss of head is found to be 1/2 of the velocity. So that's a nice question, right? So we start off 150 millimeter. Right? We want to find D2, we don't know what D2 is. Oh, right? Right? But what do you know? You know that the head loss is equal to what? Hmm?
1/2 of the velocity.
1 minus D2
Squared
Over 2
right? And they tell you that the head loss is equals to what? 1/2 of the velocity head in the 150 millimeter pipe. What's the velocity head? V1 squared on 2G.
Yes.
Yes? Remember,
Yeah.
when we write Bernoulli's principle, it's Z1 plus P1 no G plus V1 squared over 2G. This is velocity head,
Yes.
right? And the smaller pipe is your V1. This is your 0.1, 0.2. So it's 1/2 of the velocity head, right? Which is V1 squared on 2G, yes? So that's what they're saying. Yeah? That's basically what they are saying. So we have to somehow use this expression to help us, right? So we know that that's our head loss, right? So we can say V1, so we can start cancelling out some stuff here, right? Let's see. So make sure this is right. Sudden enlargement. That's correct?
Yeah.
So what we can do here, so V1 minus V2 squared, we can get rid of this, yeah?
Yes. Yeah.
Is equal to V1 squared on 2. So we have 2, 1 minus V2 squared is equal to V1 squared. Right? have now? We have two, the V1 squared minus 4, 2 V1, V2?
Yeah. Two V1, V2.
Right? Plus V2 squared equal V1. Yeah?
Minus 4.
4? Oh yeah, we have a 2, right? I'm sorry. So this should be a 4 here, right?
No, that, there. On the second.
Oh,
Instead
no,
of
no,
two
no.
V two,
I'm sorry.
yeah,
Yeah.
that. No, the two is.
2 V1
Two is
squared
okay.
minus 4 V1, V2.
Or you just distribute the
okay.
two.
Yeah, it's supposed to have a 2 in front of everything.
Yeah.
Yeah.
So this should be, I'll just put it outside, right?
Yeah.
So it's 2V1 squared plus.
Minus 4.
Minus 4.
That's 4V1, V2 plus
2.
2V2 squared. Right? So now we have V1 squared. Yes? Can we factorize that?
Okay, so that's the V2s.
We can't.
You
Well,
can't,
V1.
no, you can't because
Right?
yeah,
So we have this expression now. What do we do with that?
yeah.
Is that useful to us?
Wait, actually. Oh, good. Yeah, negative and negative. Oh, wait, yeah.
We can find another expression with Q1 and Q2.
So you're saying now we can do
Q1 and Q2.
Q1 is equal to Q2, right? So you're saying we can have what?
A1, B1.
Okay? We don't know what we don't know. We don't know how big the other pipe is.
We can simplify from. We can move the by and the for, and we know D1.
So we end up with V1 squared V1.
We know D1.
D1.
We know D1. So basically we can say what?
In terms of D, so
So we
set that
still
for
got around
D2.
two on there.
Yeah, of course.
Yeah.
In terms of D2, then.
But don't we have velocity one?
Yeah?
Trying to see if you can, if it's clear.
How are we gonna get closer
Because
to
of the lighting.
Mm-hmm.
solving our problem?
Put D2 in terms of D1.
So we know D1, it's 150, right?
Maybe do it doubles. It doubles in size.
It's a nice question. It's not a difficult question, but you should solve this, you should try to solve it.
Yeah.
For Monday.
Maybe. Is there any other information we can use?
The 1/2. The velocity of 1/2.
So we know this, right? We know that the head loss is going to be 1/2 of the velocity head in the pipe, right? We know that's your velocity head in the pipe. So what do we do?
The velocity is 150 millimeters.
No, it's in the first one.
Yeah, solve for this, solve for
Can't you
V1.
solve for V1? By isolating? Oh, I see, I see, I see.
Oh, we don't have it.
Or you can solve it from here and tell me, you know? Wait, we can find V1 just by returning.
Yeah, we just
You got actual how we know stuff like
We have it, Q is different. Yeah.
you can use them no, the question was not the concept. I said it doesn't.
We have V1, so we can solve.
Is there any assumption?
Yeah, they just want something.
Whenever we
D2.
for D3.
Can
Solve this
you
for D2.
assume?
Solve for
So
D2.
then you have something to do then. I will leave you to solve it. But what we're doing here is not the wrong
We
thing.
don't have class
Right,
now.
you halfway there.
Professor, I have like a question.
Can you assume that, I don't know if this even helps, but can you assume that the velocity head would not be half for the second section? And
Solve for
like
D2.
one,
Yeah.
try to make a relation between the two, or not really?
But if you read the question, it says you have at a sudden enlargement, the loss of head, right, is found to be 1/2 of the velocity head, right?
Yeah.
So I'm trying to understand what you're asking.
Like, in the Bernoulli's equation, the velocity for the first section is half. Yeah, I don't know, I'm confused now.
No, do you think this is probably could be wrong?
No, that's not.
Because all they're saying is the head loss here. Right? That's what they're saying, right?
Yeah.
Oops. I did write it.
This is a nice question for you to go home and solve, right? Right? It's not a complicated question. Let's look at number 4. Let's go back to number 4.
Yeah.
Right? So we have a pipe, they told us the area it carries a discharge. It says if it enlarges suddenly right? So it enlarges, right? And if the pressure in the smaller section is so and so, right, what is the head loss? Can we find the head loss?
Yes.
Yes.
Oh. So let's look at what we have. What they've given us. Right? So what's head loss in a, if we go from a small pipe to a large pipe?
V1 minus V2 squared over.
So the first pipe, our area was what?
0.093 meters squared. Area 4.
And the second one was 0.1
372.
meter squared, and they told us Q was
283 meters cubed per second.
right? So our head loss is given by
V1.
yes for an expansion, yeah?
Yeah.
So we can find V1 and V2, right?
Yes.
Yes, because remember Q is equal to A1 V1, A2 V2, so therefore V1 would be 0.283 and 0.093, and our V2 would be 0.283 and 0.372, yes?
Yes.
Right? And then once we get those values, we can plug it in to HL. Right?
Professor.
Right? And then we can use Bernoulli's now to find, right, our Z. You know it's a horizontal pipe section. So V1 over rho G plus V1 squared over 2G is equal to P2 over G. V2 squared on 2G plus our head loss, right, which was our V1, and that's V2 squared on 2G. Right? And now we want the pressure in which pipe? In the large part, right? We have P1. P1 was 4.8, right? So P1, 4.8 kilonewton per meter squared. So I'm not going to work it out, but you can see if we have P1, we have V1, we have V2, we have this, right? Yes? So our only unknown would be V2.
Regardless if there's
We just plug in square.
Alright. Now they ask us now, what is the power needed to force the water through the enlargement? How do you think we find out? So, of course, we need to overcome that, right? Right? So remember, right? This head loss is in what? What's the units of head loss? In meters, which is also equal to what?
Can you say that again? Can you say that again?
Head loss, the units are in meters,
Yeah.
which is also equal to,
Like,
okay, but it's also equal to joules per
Oh, okay.
newton,
meter? Yeah. It's,
right? Because remember, this is energy per unit weight. These things are in energy per unit weight, which is energy is in joules per unit weight, which is the same as the meter. Right? So it's really not meters, guys. It's really you're taking the energy. Remember, this is an equation that is it's really reflective of the energy you have. Right? So how do we find power? You think? We don't have time. What can we use to find it, the time?
Q is only way of time, it's Q. So we're gonna load it.
So power is what? What is it? Units of power. Work divided by what?
Time. T.
Work divided by time, right? Yeah?
Yeah.
Okay. So it's basically joules per second, right? Or kilojoules per second. Yes?
Yeah.
So I want you guys to think now, how can we go from this to this?
Multiply something by newtons per second.
A Newton is kilogram.
Whoa, it's too much.
To get power now. We're gonna work this question. We have some time. I want us to work so you guys see how we get that 737. Right? So how do we go from this?
Well, you said the meter would be,
A newton is a meter per second.
no, you said the meter is a joule.
So this is in joules per Newton or
Yes.
meter.
Yes. So the flow rate would then, oh wait,
So in order to do that, we need to do something like this, right?
yeah, exactly.
Yeah.
It's just about where you get it from.
Yes.
Yes.
So this will.
It's,
So how do we get Newton per second? You sure? But we need force.
I'm thinking of the discharge. Somewhat related to the discharge.
So you're thinking it's somewhat related to discharge, right?
Yeah.
So okay, but discharge is meter cube per second, right? So we have meter cube over second.
Yeah.
So we need something else, because this is newtons.
Yeah.
But you have the
meter,
seconds.
Yeah.
Okay. So what else?
The max.
Let's say I multiply by density now, right? If I multiply by density, yeah, what do I get? Right, but this goes, right?
Yes.
So now I have kilograms per second. Yes?
Yeah.
So I have density, right? I had Q,
Yes.
right? But what do I need? I need G now.
Yes.
Are you following that?
Yeah, to make it into.
I'll start over again. Right? So we want to find the power. We want to get to joules per second, right? Right. But remember, this equation that we have here is in joules per Newton or in meters, right? So we need to figure out a way to multiply this by this, right? So my friend here says, okay, let's start off with Q, right? Remember Q, I'll write it separately. I'll come over here. So I want to get Newton per second, that's what I want. But I start off with Q. Q is what? Meter cube per second. I have the M, I have the S, right? But this is volume. I need newtons, right? Then I say, okay, let's multiply by density, which is kilogram per meter cube, right? But you see, these will cancel, right? So I end up with kilogram per second.
Yeah.
And now to convert from kilogram per second to force per second, I need to multiply by G. Yes? By G. And G is what? 10 to the minus 2. Right? These cancel out. Yes? So what do I end up with? I end up force by acceleration is Newton, which is N over S, right? Or or basically this is kilogram meters per second over S, which is force. So basically, I need to multiply by, this is what? This was Q, this is density, this is G. So I need to multiply this by this to give me power. Make sense? Right? So when you find, let's find it, let's do the calculation. We found V1. What was V1? I already set you up here, so just tell me what V1 is.
3.04.
How much?
3.04.
3.04. What's V2?
0.76.
Everybody else getting that? Yes? Somebody double check me. Double check, Majid, please. I'm not saying he's wrong, but as engineers, we double check each other.
He's just saying he don't trust you. He don't say you wrong. He just don't trust.
No, if you go to an engineering company, you have people who are check, double check. Triple check, right?
Why did the
even
road still
triple check,
crack?
right? So now our power now is equal to HL by rho. That's your power, right? So we can find HL, which was what? V1 was 3.04, 0.76 squared on 2. So I can eliminate the G. I'll still put it in over 2 by 1,000. The flow rate was what? 2.283, right? Over 2, our G's will cancel.
Why do you multiply HL? Yeah, where did the HL come from?
Yeah.
The HL is the loss
Yes.
through the expansion.
And so that's the power that we need to provide.
Right? So they're asking you, what is the force needed to force the water through the enlargement?
Yeah.
So we need to overcome that loss.
That loss, okay.
74.99.
No.
75.
730.
I got 735?
I got 735.
Right?
Close enough.
Close enough, right? Good. Yeah?
Go back to
Right?
number
Well, they forgot to run it up, right?
So guys, when we didn't really cover this, we didn't get time to cover it. So if I'm pumping through, I'm trying to pump water through a system, I need to find all my losses. And this is really what we do. We find all the loss, the head loss, the total head loss. And we multiply by rho Q G to find the power needed to push that water through, right? But we calculated that by basically discerning, right? Using our units,
Yes.
right? So, that's our power. Right?
So, I think that's the power to push the zero from point one.
Now, I think there is some other problems here, losses in pipeline. Let me see if there's some other ones.
Yeah, it is, you have losses in
This
There's
one.
losses, and then I think it was, flow measurement. Yes.
No, I want.
No,
Yeah, so this is another one, guys.
fluids
I
and
think
motion.
you should want to try some, right? Because here in this one you have friction factors and so on. Right? Sorry?
Yes. The fluids in motion flow in pipeline.
Right? So let's look at this one, number 3. Determine the discharge through a new, right? Let's look at this one before we leave. Right. So we have a cast iron pipe, right? Determine the discharge through a new cast iron pipe. It's long, blah blah blah.
That one is easy.
Right? So,
Fluids in motion.
Fluid, flowing pipe.
how do we find that one?
So you gotta find the head loss first.
What's the discharge? Head loss was what?
Is HL equals
4.
4
F,
F
or D,
L
D
1.
squared, or,
Right? But we have another expression for loss, right?
yeah.
Yeah.
What's it? What's the other way we can write loss? No, there's another expression.
Is it V1?
FLQ squared over 3D to the power,
Over
3D to
the power of 5, right?
whoa.
Yes? Okay, so we have F, right? We have an expression for F.
Yeah.
Right, so now our head loss becomes this new F, 0.005, 1 plus D on 3.6 by L, Q squared,
Over 3D to the,
3D to the 5. Yes?
yes.
So now we plug everything in there because we have D, right?
Yeah.
Yes?
Yeah.
Yes or no?
Yes, you have both these.
You have both D1 to D2.
Right? Take D, take F,
You have
where
the
D
length.
is the diameter of the pipe in meters, right? So,
Yeah.
so in U we have the diameter, we have the length.
Yeah.
What are we trying to find? We're trying to find Q, right?
Yeah.
Right? So my Q
That's it.
equals to HL D to the 5th all over 0.005, 1 plus D over 3.6, and we square all of that.
You get 5.416.
Yes?
Yes.
Don't forget about the L.
Where's my L gonna be? On the bottom, right?
No. Wait, what?
On the bottom, yes.
Yeah.
Right? So they told us the head loss was going to be 9 meters. Right? My L is 900 meters, my D is 0.3 meters, and you plug all of this in there. Right? Don't forget this expression, this FL Q squared on 3D to the 5th. Right? Very, very useful. Right? Let's look at number 5. Number 5, let me see. Right? Right, so we have a pump, supplies water to a nozzle, right?
Wait,
Of
you finished
25
3 already?
millimeter diameter through a pipe, right? 180 meters long, right? So we have a nozzle, right? The nozzle is at a level of 9 meters above the pump. Okay, so we have to draw these things, right?
Oh, you find it, like, you probably fix it. Head of 9
Right? So a pipe,
on the,
nozzle is at 9 meters above the pump, so we have some pump. We have some nozzle, right? And then from the nozzle we go into this pipe, right? Right. So pump supplies water to the nozzle of 29 millimeters. So our nozzle here would be 25 millimeters. Then this pipe here is 75 millimeters diameter, and the nozzle is 9 millimeters. So this here, our datum, this is 9 meters, right? Taking the discharge coefficient of the nozzle, right? So this has some discharge coefficient here. I'll call it CD is 0.94. Right, the coefficient of friction of the pipe, right? 0.012. So how long is the pipe? Can you tell us? 180.
Yeah.
And they're telling us that F for the pipe is 0.012, right? And they are going to discharge, right? They say we want to find where Q is 8 dm³ per second, right? So they want the pressure. Where do they want the pressure from?
This is just the notes.
From where?
At the pump's outlet, push to the pump.
So they want the pressure at this point here.
So do we have to use the equation you just gave us? That equation?
No, what I'm trying to do, right? So this is my P, this is my P2 here, right? What's the pressure at P2?
Zero.
It's discharging to atmosphere, right? Right? So we're going to have a loss here, right? Because we're going from 25 millimeter to 75 millimeter. So we have a loss here, right there. We have a loss in the pipe and a shock loss, right? In shock loss as well as a frictional loss.
Is it that given to us?
Sorry, why is
It's given
P2
to
0?
right?
I think, like, where can we assume that it's open?
So taking a shot of the nozzle at the pipe the pipe is only 180 meters long. So obviously the water is going to come out from the other side.
okay.
You get me?
Yeah.
So this is going to be, so now we can say our P1, our Z1 plus P1 and G, right? So this would be like a -9, right?
Yes.
Yeah.
Well, no, wouldn't it be positive?
It's above.
It's in our data.
This is the data,
Yes.
Yeah.
Positive.
so positive, right? V1 squared on 2G, right? What do you think V1 is going to be? Zero. Right? V2 because you know the value of Q. We know the diameter of this pipe.
Yes.
So we know what the velocity is going to be in that pipe. Right? Plus your losses. Where we're gonna have loss, we're gonna have a loss here and in the pipe.
Yeah.
Right? And you can eliminate this already. You can eliminate those.
Yeah.
Disease.
Right?
No, you can't do these because one is
Can I drop
not.
Z2?
No, two is 0.
Huh?
One is 2
You
is
drop Z1.
1, yeah.
Right? Because that's at my
Base
data.
one.
Right? And what are we trying to find? We're trying to find P1. Yes? Right? The losses, we know we can find, we know the losses in the pipe, right?
Isn't there a pump head on the left-hand side?
Oh, what?
Sorry?
Like, a head loss from the pump?
Right here. You'll have
No, I
at
mean,
the
on
nozzle.
the left-hand side of the equation, shouldn't there be a loss for the?
No. All your losses are going to come on this side. Always.
But pump adds energy,
Yes, it's adding energy.
but,
But your losses are going to be in your system, not in the pump.
the pump is in the system.
Yes, but your pump has to overcome, for the water to get here, it has to overcome all these losses.
No, I know, so shouldn't you have losses of the pump on the left-hand side of the equation?
Can see the, no, oh, yeah. Sorry.
The pump is providing energy, yeah, you're correct. But it's going to, your water as it goes through the system, it's going to lose energy. Your pump has to overcome those losses in order for that water to get to the other side. Right? So your losses are always going to be on the other side always on the other side. Because you're going to start off with more energy and you're going to lose. You're going to lose. Right? So you actually have to put in more energy than you need to overcome those losses. Right? So I know we're out of time, but you have the coefficient of discharge for the nozzle, right? And you have, right, and you have the equation for a nozzle.
Yes.
Yes?
Yes.
For the loss, right? And you know the equation for the loss of your surface roughness in the pipe. I'll stop there, guys. Questions?